studied the concepts and applications of two kinds of polynomial functions. Linear functions are just a special kind of polynomial, and quadratic functions are another special kind of polynomial. Okay, so today we're going to expand what it means to be a polynomial. So here's the definition of a polynomial function, and it looks like super crazy and overwhelming. So the n's represent exponents, right? Those are just powers on the x. And the a with a subscript, this guy, just represents any real number. The reason we write that little subscript is to mean that's the coefficient that goes with the xtn power. So this is some like kind of crazy notation, but don't let it intimidate you, because we'll almost never look at the notation in that way. We'll be looking at more concrete examples. So if I want a polynomial function of degree 5, the degree of a polynomial is just the highest exponent of x that exists in the polynomial. Okay? So it has to be to the 5th power. Highest power is the 5th power. It's going to have 3 terms, so you're adding 3 things together. A leading coefficient of -3, and the coefficient in the quadratic term is √2. All right, so let's see if we can apply some of this vocabulary in the definition. Okay, so n is the highest power on x, that's your degree. Okay. The coefficient on the highest power of x, that's called the leading coefficient. This number at the end that has no x with it is called the constant term. This guy is called the linear term. And the one that has an x to plain old x to the first. And this guy is called the quadratic term because it's got an x squared. And then the cubic term would be the term that has a cube in it. And the term that has the highest degree and with the leading coefficient, put those together and we call that the leading term. So it's going to have 3 terms. It's going to have degree 5 and leading coefficient -3. So it would be like f of x equals -3 x to the 5th. That's my first term. Going to have a degree of 5, highest power of 5, and a leading coefficient of -3. The coefficient on the quadratic term is √2. So it's a plus √2 x squared. Just throw a coefficient on the x squared. That's what the quadratic term means. And then I think I've satisfied everything they told me except for the 3 terms. So I have to add another term in here. I could add a linear term or a constant term, whichever. Because the powers of x, you don't have to, but we typically write them in descending order. So I'll just throw on any old constant here, like a 7. So now I've got 3 terms. What does a polynomial function that has degree 0 look like? The highest power on x is a 0. Well, anything to the 0 is 1. So you throw a coefficient on there, right? So if I said, okay, well, let this polynomial be g of x equals 5, just pick any old leading term, x to the 0. But x to the 0 is just 1, so that would be g of x equals 5. A horizontal line is a polynomial that has degree 0. How about a function that's not a polynomial? X to the 3rd is a polynomial. Yep. Square root x. Yeah, so what makes square root x not a polynomial? In the atmosphere, I like that. Okay, so square root x versus x cubed. X cubed is a polynomial, right? It's just that all the other terms have 0 coefficients, right? So I would write plus 0x squared plus 0x plus 0. Now it looks like a polynomial. Right? But square root x, I can rewrite as x to the 1/2. So it does have an exponent up in the atmosphere. Right? But what about that exponent makes this not a polynomial? It's a fraction. Yeah, it's not an integer. Yep. Not an integer is what makes that not a polynomial. Polynomials have to have integer exponents. So I can write the square root of x is a non-polynomial function. Somebody give me another one that's not a polynomial. One over x and x to the 1/3 both work. So 1 over x, this is a good example, can be rewritten as x to the -1. What makes that not a polynomial? The negative, yeah. So I should have said it's not that it's not an integer, it's not a positive integer. Right? Neither of these are positive integers. That's what makes them not polynomials. Yes, but it is positive, but the word integer means whole number, not fraction. Yeah, so this is positive, but it's not an integer. This one's an integer, but it's not positive. So they fail for different reasons. -1? 1/2 is not a positive integer. No. It's positive, but it's not an integer. Right. 0 works. Yeah. X to the 0, or 5x to the 0, or 8x to the 0, those are polynomials. Constant functions. Okay, so here we have a scatter plot. It shows the consumption of natural gas in quadrillion BTUs by the United States in the decades from 1960 to the year 2000. What story does this graph tell us about US energy consumption of natural gas from 1960 to 2000? Has it always increased? No. When did it increase? Yep, 1960 to 1970, it was increasing a lot. It increased a lot, right? And then what happened? Then it decreased. Yep, then decreased from 1970 to 1990, I guess. That x-axis isn't labeled, so this is very hard to interpret the graph. Okay, so would you rather use a line to model this data or a quadratic function? Yeah, why is a line not a good choice? Yeah, a line is just always increasing or always decreasing. So a line is not a very good choice because it's not going to capture the fact that it went up and then down. But if you use a quadratic, we could model this with some kind of upside down parabola that could capture the trend in the data. Right, so I want to use a quadratic. So it's kind of we've drawn kind of a smooth, continuous curve. Looks like a quadratic. All right, so now we have oh, so I'm missing some, this picture is messed up. Ah, okay, hold on. Okay, So decreased from 1970 to 1990, and then we increased again 1990 to 2000. Okay. So a linear or a quadratic function, would either of those be a good choice for this data? No, right? Because a linear would just be straight up and down, and you wouldn't capture this trend that it went up and then down and then back up, right? So linear is not going to work. If I did a quadratic, the end behavior of a quadratic would have to be both ends down like that, and we wouldn't capture the fact that it went back up, right? So that's not a good option, right? So no, neither of those is good. So if I was going to try to fit a nice smooth curve to this thing that captures the trend of my data, it might look like that. And that thing is a cubic polynomial. So the degree of the polynomial that best fits is actually going to be a cubic. Degree 3. So it kind of looks like x cubed in the end behavior, right? It's got one arm up and one arm down, kind of like x cubed. All right, so here's another one. We have the number of AIDS cases diagnosed in the United States. X years after 1983 are displayed in this scatter plot. So really big increase, we hit a maximum, and then it starts coming down. It's difficult to find a model that's useful over long periods of time. This cubic function, 49x cubed, why is this looking terrible also? Hold on. Okay, so here's my cubic polynomial that's much easier to read. Negative 49x cubed plus 806x squared plus 3776x plus 2503. So that cubic function could be useful to model the number of AIDS cases between 83 and 91. So if this is 83 and this is 91, we have a really nice fit of the data with that cubic polynomial. But after that, we have this sharp decline, and it might not be a good model anymore, right? So if I look past 1991, which was like right here, now my cubic polynomial is a bad model because it's just going to show that the number of cases keeps going down forever, but you can't have a negative number of cases, right? So we have some model breakdown at some point. So we use this language and notation to describe the far right end behavior, right? The graph falls to the right, right? As you move to the right, the graph is just going down. And we say that as x approaches infinity, f of x approaches negative infinity, with this notation. So the behavior of the graph of a function to the far left or the far right is called end behavior. The graphs of all polynomial functions will either eventually rise or fall without bound. Okay, so as it moves far to the left or far to the right. So how can we tell what the graph of a polynomial will do? So let's look at a couple of examples and see if we can make some generalizations about what's happening. So here we have a linear function. So that's a polynomial with degree 1. The highest power on x is a 1. And the end behavior is either this or this, right? One arm up, one arm down. Okay, so in this case, this one right here, the graph falls to the left and rises to the right. And in this graph, it rises to the left and falls to the right. So if I was going to fill in the end behavior for this graph right here, I would say as x approaches negative infinity, what's happening to f of x? It's going up to infinity. And as x approaches infinity, what's happening to the y values? Negative infinity. All right, and then let's look at some a quadratic function with an even degree. So for this one on the left, we've got both arms up. Okay. So as x approaches negative infinity, the y's approach positive. And as x approaches positive infinity, the y's approach positive infinity. So the graph rises both to the left and to the right. And then I've got a quadratic that opens down, and the graph falls to the left and falls to the right. So my end behavior in both cases is negative infinity. Both arms down. All right, how about these cubic functions? Which end behavior does the cubic function match, the linear or the quadratic? The linear. It's got the same end behavior. It does something kind of different in the middle, but if you ignore the middle, it's got the same end behavior, one arm up, one arm down. So the middle is different, but the stuff at the far ends looks exactly the same. So in this case, as x goes to the left, y goes up, and as x goes to the right, y goes down. All right, now I've got some fourth degree polynomials here. Part of this must have gotten cut off. This must look like something like that. Okay. So in this quartic function, does it have the same kind of end behavior as linear and cubic, or as quadratic? Quadratic. It's got a both arms up end behavior. Touchdown, right? Or negative touchdown. So this one, these are both negative infinity. Falls to the left and falls to the right. So we can kind of try to generalize and say when the degree is odd, right? Because when it was 1 and when it was 3, the end behavior looks the same, one arm up, one arm down. And when the degree was even, right, 2 and 4, it was both arms up or both arms down. So that actually turns out to be the final conclusion, okay? For an odd degree polynomial, so that means if its highest exponent is odd, we have graphs with different end behavior at each end, right? One end goes up, one end goes down. For an even degree polynomial function, we have graphs with the same end behavior, both arms up or both arms down. Right, okay, so here's sort of the general definition of a polynomial. Something times x to the n plus something times x to 1 degree smaller. When n is odd, right, when the highest exponent is odd, 1 or 3 or 5 or 7, right, if you have a raised to the 5th or raised to the 7th, raised to the 9th, etc. When n is odd, you're going to have one arm up and one arm down, different end behavior on each end. And the end that's up depends on the leading coefficient, okay? If the leading coefficient is positive, the graph falls to the left and rises to the right, right? That's leading coefficient positive. Leading coefficient negative, left arm up, right arm down. And then for n even, when the leading coefficient is positive, it's both arms up, negative, both arms down. All right, so let's come back to this cubic function that models the number of AIDS cases 1983 to 2008. And we're going to use end behavior to determine why this model is not appropriate in the long run. Okay, so what is the sign of the leading coefficient? Or what is the leading coefficient? Negative 49, yeah. So my leading coefficient is negative 49, which is negative, right? Smaller than 0. Okay, what's the degree of that polynomial? 3, which is odd, right? So I know the end behavior of this polynomial is going to be one arm up, one arm down. And in fact, it's the left arm that's up. So it would look something like left arm's up like that. Bunch of stuff happens in the middle that I don't know what it looks like. And then the right arm is down, right? So why is it that this thing is a bad model for the number of AIDS cases? Yeah, you can't have a negative amount, and the end behavior of a cubic will always go down towards negative infinity in the long run. Okay, so the end behavior of this graph over time, as we move to the right, we would say as x approaches infinity, f of x approaches negative infinity. Okay? So as time marches forward, this says that the number of cases of AIDS will go towards negative infinity, which is impossible. All right, so the values of x for which f of x equals 0 are called the zeros of a function. Also known as what? When you look at the graph, what are they known as? X-intercepts. Places where the function equals 0 are x-intercepts. So we also call them zeros sometimes. We use those interchangeably. So if I want to find all the real zeros of f of x equals x cubed minus x squared minus 2x, that means find all the places where the function equals 0. So I put in a 0 for f of x. Any ideas on how to solve that equation? Well, it's a cubic, so I can't use the quadratic formula yet. Factor out an x. Yep. So if I factor out an x, I would have x squared minus x minus 2. Does x squared minus x minus 2 factor any further? X minus 2, x plus 1. So that means that my zeros are what? 0, 2, and negative 1. Set each of these factors equal to 0 and solve. Which means I have x-intercepts. The corresponding x-intercepts are, the only difference between zeros and x-intercepts is that x-intercepts are points, so they have 2 coordinates, an x comma y. And when you talk about zeros, you just list them, the x values. So the x-intercepts in this case are 0, 0, 2, 0, and negative 1, 0. Because if you're on the x-axis, the y-coordinate is always 0. All right, so if I want to verify the zeros of this thing, I could use my graphing calculator or GeoGebra. Okay, so I've got a function f of x equals x cubed minus x squared minus 2x. Oops, I did that wrong. It's supposed to be x cubed. There we go. Okay, so does that have the expected x-intercepts that we calculated algebraically? Negative 1, 0, and 2. Yeah. Okay, so let's look at the end behavior of the graph near the 0, x equals 1, right? So if I look at my graph on GeoGebra, okay, so here I've graphed f of x equals x minus 1 squared, right? This is my function, which is the graph of x squared shifted 1 to the right. Okay, so if I just zoom in on this x minus 1, right? The factor x minus 1 occurs twice, right? Because if I were to set this equal to 0 and solve it, I would say, oh, well, that means x minus 1 times x minus 1 equals 0. And when you set each factor equal to 0 and solve, you're going to get x equals 1 as a 0 2 times, right? So you get x equals 1 or x equals 1, right? So when that happens, you say that 1 is a real 0 that has multiplicity 2. Just means that it happens twice, multiplicity 2. And when you have zeros that have multiplicity 2, you're going to get this sort of bounce-off effect, right? Where it comes down and just hits the axis and comes back up instead of going right through it. So in this case, on the right, I graphed x minus 1 cubed, right? And if I were to try to set that equal to 0 and solve, I would get x minus 1 times x minus 1 times x minus 1 equals 0. Set each factor equal to 0 and solve it, and you'd get x equals 1 or x equals 1 or x equals 1, right? So in that case, we would say that 1 is a real 0 of multiplicity 3. because it happens 3 times. And this time it went through the axis, right? It didn't bounce off, it went through. So what happens is if the multiplicity is even, then the graph touches the x-axis and then bounces off, right? And if the 0 has odd multiplicity, then the graph crosses the x-axis. So let's do another example with this. So here's some graphs of polynomial functions. We want to find the zeros and state whether the multiplicity is even or odd. So my first 0 in this picture is at -2, right? That's the first x-intercept. Does it have an even or an odd multiplicity? Odd, because it goes through the axis. Right? So that means it might be a factor once or 3 times or 5 times. We don't know. We just know it's odd. How about at 0? Same, odd. It goes through the axis, so it's odd. All right, and then at 3, we have a real 0, and it's also going to have odd multiplicity. All right, let's do a trickier one. Oh, sorry, a possible equation for this thing. Well, let's see. If x equals -2 is a 0, then that means that x plus 2 had to have been a factor, right? Because when you set each factor equal to 0 and solve, if -2 is a solution, x plus 2 is a factor. And x minus 0 had to have been a factor, or just plain old x. And x minus 3 had to have been a factor if 3 is a 0. And then the exponents tell you about the multiplicities, right? So since these are all odd, I'm just going to put 1s, right? Because this is a possible equation, right? I don't actually know what those exponents are. I just know that they're odd. Could be 3s, could be 5s. And what does the end behavior tell you about that a value? Positive or negative? Positive, I think. Yeah. Yeah, if it rises to the right, that's a positive leading coefficient. So a is positive. All right, let's look at a trickier one. So before I start analyzing the zeros, the end behavior of this thing is both arms up, right? So what do we know about its degree? What the degree isn't positive. What is positive? The leading coefficient is positive. Yeah. So I know a has to be positive. What do I know about the degree? Even. Yeah. I know the final degree has to be even to get a both arms up or both arms down. Okay, let's look at the zeros. My first 0, when I look furthest to the left, my first 0 is at x equals -3. It's a real 0 of the function, and what is its multiplicity, even or odd? Even, because it bounces off the axis. So it's going to be at least a multiplicity 2, maybe 4, maybe 6. Okay, next 0 happens at -1. Even or odd multiplicity? Odd. And then my next 0 happens at 1. Even. And then I've got another one that I didn't write down, right? So my next 0 is at x equals 3. And it is odd because it goes through the axis. So a possible formula for this thing, if x equals 3 is a 0, that means x minus 3 had to have been a factor. So I'll put in x minus 3, and that one's odd, so I'll put a 1 for the exponent. If x equals -3 is a 0, that means that x plus 3 was a factor, and that has an even multiplicity, so it has to be a factor at least twice. I could also put a 4 or a 6 there, I don't really know. And then x equals -1 is a 0, that means that x plus 1 had to have been a factor, And it has odd multiplicity, so I can put a 1 there. I could also put a 3 or a 5, I don't know. I just put the smallest one to make it as simple as possible. Yes? Unless it says, sometimes the directions say, like, make the degree as small as possible. Yeah. All right, and then my last 0 is a 1, which means if 1 is a 0, x minus 1 had to have been a factor. And it has even multiplicity, so I'll put a 2 there. Yeah, so the degree of this thing, if I were to multiply this all out, I would have an x to the first times x squared times x squared, right? So when you multiply those all together, you get x to the sixth, right? That's the degree of the entire polynomial. It's a 6th degree polynomial, and that matches your both arms up and behavior. Okay, why don't you guys try one? I feel like I've been talking for too long. So we've got a polynomial. It's already all factored for you, so you don't have to do any work to factor it. Just find where it crosses the x-axis and determine its multiplicity. Okay, so to find the zeros of f, you set f of x equal to 0, and we try to solve it, right? So I've got this whole thing, 1/9 x plus 3 squared x plus 1 times x minus 1 squared times x minus 3, and we're setting that equal to 0 and trying to solve it. So then you set each factor equal to 0 and solve it. So if I have x plus 3 squared, that's x plus 3 times x plus 3, which means I'm going to get x equals -3 as a 0 how many times? Twice. Yeah. So that's my multiplicity too. Yeah. Which I can then classify as even. Right? Okay, so then my next factor, my x plus 1, when I set that equal to 0, I get x equals -1. And the multiplicity is 1, because that's just a factor one time, so its multiplicity is 1. For x minus 1 squared, set that equal to 0, and you get x equals 1 is a 0, but it's a 0 2 times. So we say that's multiplicity 2, which is even. All right, and then the last factor, x minus 3, you set that equal to 0, you solve, you get x equals 3. The multiplicity is 1 because it's just a factor one time, and that's odd. Okay, so let's start to try to think about what the graph of this thing looks like. What degree is this polynomial function? 6. How do you know it's degree 6? Yeah, so I'm multiplying all these things together. This is x plus 3 squared times x plus 1 times x minus 1 squared times x minus 3. And when you're multiplying like bases, you add the exponents. Everyone remembers that rule, right? So this is just x squared times x times x times x, times x squared times x. Which would come out to an x to the 6th. That would be the highest power of x. There's lots of other terms in there too, but I only am caring about the highest power of x right now. So I would say this is a 6th degree polynomial, which means what about its end behavior? Either both up or both down, right? Right? It's either like that or like that, depending on the sign of the leading coefficient, right? The sign of the leading coefficient in this case is, the leading coefficient is 1/9, yep, which is positive, right? 1/9 is positive, so that means it looks like this, right? That's my end behavior. So let's try to kind of sketch what this graph looks like without using any kind of technology. I know its end behavior looks like this. Goes up both ends. I know it has zeros at -3, -1, and 3, and 1. -3, -1, 1, and 3. So if I try to like fill this in from left to right, I've got to come down from the end behavior towards this 0 that happens at -3. And the fact that that 0 at -3 has even multiplicity, what does that tell me about what the graph is going to do there? It's going to hit it and go back up. Yeah, so this is going to come down towards my 0 at -3, and it's going to hit it and go back up. So then in between -3 and -1, it's going to have to turn around to come back down towards that 0 at -1. And that 0 at -1 has odd multiplicity, which means it's going to go right through the axis this time. So this is going to have to come back down to go to that 0, and it goes through the axis. Then my 0 at 1, it's going to come up and go back to my 0 at 1. And this time it's going to bounce off because it has even multiplicity. So I come back up and it's going to bounce off. And then my last 0 has odd multiplicity, which means it's going to go right through the axis, which is good because it has to end up going up in the end, right? So this is going to turn around and go back up and meet the end behavior. This is the general shape of the graph. We don't know exactly how high or low these turning points happen at or where they happen, but that's sort of the general gist of what that graph looks like. Yeah. No, the only way you know whether it goes through or bounces off is the multiplicity of the 0. Even bounces off, odd goes through. Yeah, Tyler.
Just like the 1/9 scale, there's just negative or positive.
Yeah, if that 1/9 is representing a vertical stretch or a shrink, right, of a 6th degree polynomial. But we're not really going to use it for that right now. We're not going to be that detail oriented about it. Yeah, right now we're just saying negative or positive. Yeah, because if it were negative, this whole thing would reflect over the x-axis, and then you'd have the negative touchdown. All right, one more. Turning point. Okay, so what's the degree of this function? Oh, so, okay. Okay, so somebody said 5. And I know that you got 5 by adding all the exponents together. Why is that not what you do in this case, even though that's what we did in the last problem? There's no multiplication here, right? In the last problem, I was multiplying all these things together. And when you multiply like bases, you add the exponents, right? In this problem, in number 12, everything's already multiplied out. This isn't in factored form, right? So I'm just adding a bunch of terms together, and the degree is the highest power that appears. So the degree of this guy is 3. So what we were doing before is we were trying to multiply it all out without doing all the work of multiplying it all out, right? I was just kind of imagining if I were to multiply this all out, the highest power of x that would appear would be a 6. Now I don't have to do any of that work, it's just given to me. How many real zeros does this function have, according to the graph? 3. Coincidence, degree 3, 3 zeros. How many turning points does this graph have? 2 places where the graph goes increasing to decreasing or decreasing to increasing, local max or local min. What happens at each turning point? The graph turns around, or we go increasing to decreasing or decreasing to increasing. So we have degree 3, 2 turning points. So my general conclusion here is that if the polynomial has degree n, right, for whatever the degree is, the graph will have at most 1 fewer than that turning points, Like in our example, it had degree 3 and 2 turning points, 1 fewer. And it will have at most n zeros. So in this case, it was degree 3, 3 zeros. But it could have fewer, right? It could have fewer. Like think about x cubed. Its graph looks like that. What's the degree of x cubed? 3. And how many zeros does it have? 1. Real zeros, or 1. And how many turning points does it have? None. Right, so the most you can have for zeros would be the same as the degree, and for turning points would be 1 fewer than the degree, but you can have less than that. Right, that's all I got.